So today we're going to be taking a look at the calculus of chemistry kinetics. So this is intended to supplement the textbook chapter 12 for AP chemistry. And in chapter 12, the focus is looking at how we can model the rate at which a chemical reaction proceeds as a function of time. Now, in order to actually do that formally with more rigorous mathematics, you would actually require the use of calculus. But because AP Chemistry does not require calculus in order to take it, most AP Chemistry textbooks are going to sort of work around the calculus and kind of just present the solutions to the problems without much explanation as to where the solutions came from. So the point of this video is to kind of elaborate on that and show you how we would use calculus to formally present some of these solutions, and also to give you a better idea of the assumptions we make when we model these equations and how we can use statistics to analyze this type of data and these solutions in the real world. So let's first discuss the general concept of the type of problem that we're solving here. So in a chemical reaction, you have reactants and they form products over time. Now we assume that the speed of the reaction at any time is a function of the concentration of each component, similar to bank interest. So the more you have of a particular reaction, the more that's a reactant, that's going to impact how quickly a reaction takes place. Our ultimate goal is to be able to predict the concentrations of any of the items in the reactions as a function of time. So we know at any time in the reaction how much to expect there is of any of the elements within the reaction. Now, depending on the actual reaction, this can be very tricky to model because we could have a lot of variables going on, and it can be very hard to do in theory. So in order to account for that, we're going to simplify the model by quite a bit in order to actually be able to generate some solutions. Our first assumption is that these reactions that we'll study have only one reactant. Now in your class you should have been dealing with different reactions that have multiple reactants. The problem with that is now we're dealing with a situation where those concentrations might independently and interactively impact the rate of the reaction. And that gets very, very complicated. So we're going to assume that all of these are reactions that have only one reactant. So a very small subset of the ones we've looked at so far. Our second assumption is that the rate of the reaction depends only on the concentration of the sole reactant. In other words, there are really no impacts of a reverse reaction. In an actual chemical reaction, you could have the reaction going in either direction at any given time, and then when the reaction is pretty much no longer going in either direction, we often say that the reaction has reached equilibrium. And the problem with this is that if the reverse reaction has an impact, then the concentration of the reactant could start doing different things. So here we're assuming that the rate of reaction depends only on the sole reactant, so the reverse reaction impacts are going to be negligible. And these are pretty heavy simplifications based on what could happen in a pretty typical chemical reaction. So this is how the book formally states the mathematical problem that we're looking at here. We assume we have a chemical reaction where a single reactant is making products, and we just call that reactant A because that's just a stand-in name. And in the book, it says that negative delta concentration of A over delta T is equal to some constant K times the concentration of A to the N, and we call N the order of the reaction, and it's just the exponent on the concentration of A in the equation. Now, you will also see that there is a negative on the left side. So the way we write this, we always want K to be a positive constant. That's just the way we like to do it, which means that in order for this equation to be true, delta concentration of A over delta T is always going to be negative. In other words, what that means is over time, the concentration of A is expecting to always be decreasing as the reaction proceeds. That makes sense because A should be forming products. So the concentration of A should be going down as time increases. Now, you'll also notice that delta, you should recognize that from other uses in different classes, but I'm thinking mostly of algebra, where you would use that to say delta y over delta x to talk about slope of a line or average rate of change. We use it for a finite difference, and this is what we do to avoid calculus. So AP Chemistry textbooks will usually use the delta in order to not have calculus notation in here because it's not a prerequisite for the course. For those of you who are in calculus or have taken calculus, you should start to be able to predict what those deltas are going to turn into. And AP Chemistry textbooks will discuss solutions to these problems for n equals 1, 2, and 0 for your first, second, and 0 order. And when I say discuss, it kind of means they just sort of say what the solutions are. They don't bother actually deriving them. They call the solutions integrated rate laws. And once again, if you know your calculus, you should start predicting why we call them integrated rate laws. So for the first order solution, this is it. The natural log of the concentration equals negative kT plus the natural log of the initial concentration. For n equals 2, we have the reciprocal of the concentration at any time is equal to kT plus the reciprocal of the initial. And for n equals 0, this is the only one you see where the concentration of A is isolated on the left side. We have our linear relationship of negative kT plus the initial concentration. And we will be discussing the sort of weird format that these equations are in and why that matters later in this video. Now, to actually solve these problems, we're going to have to write them formally as differential equations. So I'm going to bring back some more of our typical mathematical notation here. So I'm going to let y of t represent the concentration of our reactant A as a function of time. So I just want to bring in the y because we're more used to seeing differential equations with y's in them. And then I can write the equation, the general equation, as dy dt equals negative ky to the nth power, and again, n is our order of the reaction. Also notice that I move the negative sign because typically when we write differential equations, we try to write the derivative isolated, so I just move the negative so that it would work. We're also always going to have the initial condition that the concentration at time 0 is what we call the initial concentration, or concentration A sub 0. Now I'm going to go in a slightly different order than the books typically do. I'm going to start with 0 order because you should be able to see how the mathematical processes build as the value of n changes. And so we start with n equaling 0, which just gives us a very simple differential equation, dy dt equals negative k. That's another way of saying the derivative or the instantaneous rate of change of our reactant at any time is constant. And you should be able to predict what type of equation has a constant derivative. And we always start by separating the differential equation because it is separable, and that allows us to take the integral of both sides, hence our integrated rate laws. And this gives us the solution, the general solution, y equals negative kt plus our arbitrary constant. And what do we do with the arbitrary constant? We put in our initial condition, where the initial concentration of A sub 0 is equal to the value of this function when t is 0. This tells us that C is just the initial concentration of A, and that gives us a final equation of y equals negative kt plus the initial concentration. So here I'm leaving the dependent variable as y, but you should see in the original rate laws that they just replace that with just the concentration of A. I'm just leaving it in our more typical mathematical notation. Once we switch to a first order, then we really actually get a true differential equation of the type that really requires calculus to solve. So the first order is going to look like this, dy dt equals negative ky. And then we can separate the differential equation by dividing both sides by y and writing it as 1 over y dy equals negative k dt. This allows us to integrate both sides to get that the natural log of y is equal to negative kt plus our constant. Once again, we can put in our initial condition. When t is 0, y is the initial concentration of A, and that's what gives us our constant to bring us the final equation of the natural log of y equals negative kt plus the natural log of the initial concentration. And as we saw, I'm leaving it in that form for now, and we will discuss why that is in a little bit. Finally, the second order. we write it formally as dy dt equals negative ky squared. Now, if you want to test your ability to solve differential equations and you want to try doing this one on your own and later skipping ahead to see if you get the right answer, you could do that. But otherwise, I'm going to go through the steps. Separating the differential equation to get 1 over y squared dy equals negative k dt so that I can integrate both sides. Now, normally in calculus class, we would write the left side as y to the negative 2, so it's a little easier to see how to do the power rule. I just sort of skipped that step and went to that the integral of 1 over y squared is negative 1 over y. And integral of the right side is the same as it's been the last two times. Now notice there's a negative on both sides, and we haven't determined what c is yet. So I can just clean that up by multiplying both sides by the negative. And since I don't know what c is yet, I don't really need to worry about how that would affect the sign, because I haven't solved for it yet. Now that I have it in this form, I am going to solve for it now. So I'm going to plug in t equals 0, and that y is the initial concentration of A. This tells me that c is 1 over the initial concentration, and that gives me the final form of 1 over y equals kt plus 1 over the initial concentration of A. So before we move to the data analysis piece, I want to talk about why we keep the laws in this form in the AP book. Because if you're used to the work you do in calculus class, you don't typically leave the equations like that. You always end up isolating the dependent variable in the solution. So what would that look like? Well, for our first order equation, we have that the log of y equals negative kt plus the log of the initial concentration. But if we were to take the anti-log of both sides, or sometimes we say raise e to both sides, in order to isolate y, we can end up rewriting this in our more familiar exponential form of y equals the initial concentration of A times e to the negative kt. Now that's something that should look very familiar to you from your work in a calculus class. We can also do something similar with our second order, which we can change it from this form to kt plus 1 over the initial concentration by taking the reciprocal of both sides. So by taking the reciprocal of both sides, it ends up looking like this. But even though we do this in calculus class, we don't typically do it here. The book tends to leave it in linear form. And you might think that that is just to avoid the additional mathematics and algebra of putting it like this, but there actually is a better reason, and we're going to talk about that right now. So what I have here on this Desmos page is a problem from the book where they gave a sample of concentration of a reactant in molarity as a function of time in seconds. And these numbers here that you see in these first two columns are the numbers that are given. That makes the scatter plot that you see here, the green dots. And as you can see, that looks pretty nonlinear. And if you recall, a linear result would be a zero-order reaction, where the reactant is just, its concentration is just decreasing at a constant rate. Since that's not happening here, we should think that this is either a first or second order reaction. Now in my table, I also have a column where I took the log of the concentration here, and you can see those are all negative values. And I also took the reciprocal of the concentration, which is all positive values. So what I want to do is see what the scatter plots would look like if I did the log of the concentrations versus time and the reciprocal. So the log of the concentrations would involve looking at the possibility that this is a first order reaction. So to see what that scatter plot looks like, I'm going to change my y values to go from -7 to -4 because all the logs are negative. So this is what that scatter plot looks like. And as you can see, it looks more linear than the initial scatter plot with the zero order, but there still seems to be a slight curve here. Now, because this is we're testing for a linear relationship, we can do linear regression on this and take a look at the residuals and do other techniques you might talk about in AP statistics. But let's take a look at the scatter plot for the reciprocal of the concentration as a function of time, and that's looking at the possibility that this is a second order reaction. And if we take a look at the numbers here, they go from 100 to 480. So I'm going to change my y values again, and I'm going to, let's say, make them from 0 to 500. And this is what that scatter plot looks like. And as you can see, that looks very linear. This looks even straighter than the first order scatter plot. First order was better, but this second one looks very, very linear. Now, to confirm that this is what we think it is, let's go back to the initial scatter plot of just the actual concentrations as a function of time. So here's that scatter plot here. And I'm going to first try to match an exponential equation to it, which again would suggest a first order solution. So if I try to match the exponential equation to it, you can see that there is a curve to a first order because it's exponential decay, and that's pretty good. But you can also see that the points kind of have this dip above, be above the curve, then dip below it, then be above it again. And that type of curved behavior around the solution kind of leads us to think that the first order may not be quite right. It has the curve, which is better, but the points seem to be doing something slightly different. So I'm going to turn off the first order equation, and now I'm going to have Desmos try to match a second order solution to it, which is going to be of the form of 1 over kT plus a constant. And when I do that, you can see what happens. We get a solution curve that very closely matches the points. So that aligns with what we saw earlier when we saw that the scatter plot of the reciprocal as a function of time looked very, very much like a straight line. So by allowing these rules to stay linear, we can do linear tests on them statistically to get the best idea of what type of reaction we're dealing with. Because statistical analysis has a lot more tools for evaluating potential linear relationships than they do for nonlinear relationships. So if you're thinking that that's, that the reason why your chemistry textbook leaves the integrated laws as linear functions is to just avoid the algebra of transforming them, it's a little more complicated than that. It's really that the linear form is much better for data analysis if we were actually taking data from our lab and trying to see what was going on. So hopefully this has given you a little more insight into how these solutions work, how we find them, and why we leave them in the forms that we do. Also, you should now have some insight as to how these problems could potentially get more complicated and why we only look at it at this introductory level at this point in time. But hopefully this has helped you and given you some more insight, and I will see you later.